Thanks everyone for joining us. We're glad to have our Palo Alto Parkinson support group meeting today, combined with the Stanford Deep Brain Stimulation support group meeting. Haven't had one of those in a while, so we're glad to kick off another one of DBS support group meetings with a fantastic speaker who doesn't speak very often. So we're so glad to have her with us today. It's Dr. Helen Bronte-Stewart. She's been at Stanford for quite a long time now. And as I mentioned in the promotional materials for today's meeting, she's really a pioneer in adaptive deep brain stimulation. So we're glad to have her here today, and you take it away, Dr. Bronte-Stewart.
Great. Thank you, Robin, and thanks for that kind introduction. And hello, I wish we were all in person, but hello again to everybody. I'm going to talk about adaptive deep brain stimulation and sort of how we get there. And please feel free to ask questions and put them in the Q&A. I can't see them with my right now, but they'll be monitored. So I want to dive straight in and talk about deep brain stimulation as a brain pacemaker. So currently, the way we use it is what we call an open loop brain pacemaker. And what do we mean by that? Well, if we go back to the analogy of cardiac pacemakers, there was a time when basically these were open loop, meaning that wires were inserted into the heart and the heart was paced. Now that helped people who had such a low heart rate, they basically couldn't stand up, but it didn't sense the heart's rhythm. And so there were often extreme complications of other arrhythmias that would develop. Currently, cardiac pacemakers have evolved into demand-based or closed-loop devices that can sense the heart's electrical rhythm. They can be activated on demand, say for bradycardia, when the heart rate goes below a certain threshold, that's the only time they turn on. They can now sense and learn normal from abnormal heart rhythms so that they don't cause other arrhythmias, as happened in the early days. And they use what we call optimized, adaptive, and automated stimulation algorithms customized to the patient. When we talk about deep brain stimulation or brain pacemakers, until recently, clinically, they still operate in an open loop fashion. And that means that they can't act based on sensing the brain's electrical rhythms. And in fact, until recently, we actually couldn't sense the brain's electrical rhythms through these pacemakers. And now you know the Percept system can. They certainly cannot sense and respond to specific symptoms such as tremor, bradykinesia, gait impairment, nor to whether the person's asleep, whether they're still or whether they're active. And importantly, they can't respond to the medication levels and what their influence is on brain rhythms. They're continuous, which means they're on all the time, and they use a one-size-fits-all parameters for everybody. So you can see that there's a big gap here between cardiac pacemakers and where we currently are with brain pacemakers. But if we're going to talk about developing a closed-loop system that responds to either neural signals or perhaps to movement signals, whether they be generated from a smartwatch or from wearables on the legs for gait, say, we need to determine the neural and the kinematic or the movement signals that are actually relevant to the pathological motor behaviors, to the movements that we don't want. And so an analogy back to cardiac pacemakers is, if they used algorithms which drove the heart in the wrong direction, you could kill someone. So you really want to make sure that you have determined initially what are the electrical rhythms that are responsible for the problems you're trying to solve. So this is something that we and others have been doing for many, many years that have led to the development of adaptive deep brain stimulation. So I'm going to go through a little bit of that to kind of orient you as to why we use the signals that we currently use in our first adaptive deep brain stimulation studies. So the first thing we have to do if we're talking about movement problems is we have to measure movement. And for those of you who have been kind enough to work with us in our lab, you know that we've developed several quantitative and objective ways of measuring movement. So one of them is what we call quantitative digitography, where the person does a simple repetitive alternating finger tapping task on what we call tensioned engineered levers that look remarkably like piano keys. And out of that comes a trace where you can see the person pressing down on the lever and the lever coming back up again, and they do this with the 2 fingers. And actually from that, we can determine metrics that correspond to all the motor problems in Parkinson's disease. We also use wearable sensors, and we've been using these for quite a long time in my lab. So now they are basically what we call inertial measurement units. They can measure acceleration, velocity, and position. And here you can see somebody who's off their therapy, who's trying to do a repetitive flexion extension task, and unfortunately is having great difficulty doing this. And you can see that we pick this up in what we call the angular velocity trace. So here we have nice ways of measuring the movement in order for us to understand what signals are relevant to the movement problems. Now, we've also developed ways to measure gait. And the first task we developed to measure freezing of gait was done by Julie Nantel in my lab using a stepping in place task on these force plates, which we've now shown that if you put wearable sensors on these, you can also detect these abnormalities of movement just stepping in place without the force plates. Then we developed something called the turning and barrier course, which mimics the situations in normal life that people find make it difficult to walk smoothly, and that's going through narrow doorways, going through tight corners, and especially if what we call optic flow is limited, meaning that say they're in crowds and your brain can't kind of project how to walk. So these are 2 tasks that we use that in the clinical setting that actually elicit abnormal movement and freezing of gait. And in the turning and barrier course, people get up and do 2 ellipses around those barriers, and then 2 figures of 8, sit down and get up and do it again in the opposite direction. And during this talk, I'll show you some of the ways we do this and the metrics we get out of it. And here you can see that currently we have 11 sensors on the person, but the ones we're going to be talking about are really reflecting the sensors that are on the lower leg measuring gait. So as you know, deep brain stimulation or brain pacemaker comprises very accurate location of the target of interest, which are in these deep gray nuclei of the brain, some of them extremely small, like the subthalamic nucleus, which is about 160 cubic millimeters. And the subthalamic nucleus in that tiny little volume actually serves not only sensory motor networks, but also involves mood, cognition. And we want to make sure that if we're trying to correct movement, we put these brain pacemaker leads or these deep brain stimulation leads very accurately in the sensory motor region, or accessing the sensory motor network of the brain. And to do that, we have very accurate targeting initially, and then we also do what we call microelectrode recording. We move the limbs and we listen through the oscilloscopes and through our headphones for the responses of the cells as we move the patient's limbs. And so this allows us to place these leads very accurately in the brain. And these are some reconstructions of our leads in the subthalamic nucleus done by Kevin Wilkins in my lab. And you can see how even if they're coming in at different angles, which the neurosurgeon will do to avoid structures they don't want to go through, you can see that they land up nicely in this tiny little nucleus in the sensory motor region. So that's really, really important to get the best result. So one of the things that's really helpful by placing deep brain stimulation leads in these deep structures, such as the subthalamic nucleus, which is represented here by this red structure, is that, as we said, we do some fine microelectrode recording of single unit recording. And from that, that helps us put the lead in the correct place. But we can also get a sort of more global recording of network activity called the local field potential. And I'm going to go through this and break this down as to what this is, because this is the way of measuring brain rhythms, just like we measure cardiac rhythms. So what is the local field potential? Well, here's another raw trace of the local field potential measured from the subthalamic nucleus. And when you look at bumps here, these are sort of fluctuations in amplitude of the signal, and they're occurring at different frequencies. So here's a frequency here. You can see this oscillating frequency. And here's another higher frequency here, spikes going at different frequencies. And so when you map this on a different kind of graph where you're looking at frequency here along the x-axis, and you're looking at the power or how much of power in that signal is in that frequency band, what we call the broadband or 1/f signal is what the normal brain wants to do. So you see, just like any other communication system, you see a nice broad representation in different frequency bands. And using this, the brain can transiently increase its power in any frequency band and transiently synchronize one area of the brain with another. And this leads to very effective and very flexible brain transmission and information coding. So an analogy of this is if you're in a crowd and there's sort of a hum of conversation going on, but no single conversation is dominating, and you can hear yourself speak to your neighbor. If you encounter something like this with this big red peak over the 1/f curve, this is what we call exaggerated neuronal oscillatory activity with increased synchrony that doesn't go away. And this will appear as a peak in a specific frequency band. So here I'm outlining this frequency band between about 8 and 30 hertz, and you can see there's huge power here in the signal. And what that tells us is that in the region we're recording from, the information processing is basically being jammed in this frequency band, not allowing other frequency bands and other transient synchrony to go on. And a good analogy here is if you're in a crowd, maybe chanting a protest or something, and they're chanting the same thing over and over again, and it drowns out any other conversation. And so in the brain, this is drowning out information processing. That means the brain can't process information the way it would like to. And this indeed is what we call the alpha beta or the beta oscillopathy in Parkinson's disease. And just like we talk about neuropathies, this is a disorder of brain oscillations or brain activity, and we call it in the frequency range that we see it, which is called the alpha beta range. So a lot of work has gone into the relevance of this abnormal rhythm in Parkinson's disease over the last 20, 25 years. And it's very well known now that it's actually evident in the sensory motor network across both sides of the brain in Parkinson's disease. And so this sensory motor network appears to be sort of locked in this rhythm, at least in the off therapy state. The degree of this rhythm increases as the disease progresses, and we've shown that it's greater in the more affected subthalamic nucleus, corresponding to the more affected side of the body. It's related to what we call the hypokinetic aspects of Parkinson's disease, such as bradykinesia and rigidity, and it's actually attenuated during resting tremor. Importantly, it's attenuated in a dose-dependent manner, and I'll show you this a bit more in a minute, by both deep brain stimulation and dopaminergic medication. And the degree of attenuation is related to the degree of improvement in bradykinesia and rigidity. So now all of a sudden you have a signal here that if you use that to drive your therapy, the more you drive the rhythm down, the greater the improvement in motor signs. So here we have our first relevant neural signal to use in closed loop or adaptive deep brain stimulation. There's a little twist to this. This beta rhythm that I've been showing you is sort of the average of power over time. And the beta rhythm is a normal rhythm in our brain. We all have it. That's what we want. We want it to be there. It's sort of an idling rhythm that allows us to say one thing without a lot of other sort of words coming into what we're trying to communicate, do one thing without a lot of other movements contaminating that movement. So we need the beta rhythm, especially in the cortex. And one of the things the very prominent neuroscientist, Anne Gabriel, pointed out is in the healthy non-human primate, this beta power was fluctuating normally in these very short 40 to 120 millisecond bursts. And she suggested that perhaps the problem in Parkinson's disease is not that the beta rhythm is actually there, it's just occurring in these longer bursts. So it's disrupting the information processing by being around for longer than it should. As I said, the brain likes to transiently synchronize different parts together in different frequency bands, but what's happening in Parkinson's is maybe it's hanging around too long. So what we did is we went back and we looked at our neural signal across the frequency spectrum, which is shown here, and we basically divided it into 6 hertz overlapping bands. And we looked at this, and we can synchronize our neural recordings with our motor recordings. And this is somebody doing that stepping in place task. And if you looked in from the side here, first of all, you can see that we do have these bursts going on in different frequency ranges at bands at different times. And if you look from this side on, you'd see that they were hanging around for longer periods of time. And we call these beta bursts. And so we went back and we looked at our own data, and we showed, in fact, it was very true that in the resting state in Parkinson's disease, these beta band bursts showed increased power and quite prolonged durations, now up to a second and over a second, as opposed to 120 milliseconds. And other groups showed, in fact, that if you only looked at these high frequency, longer duration beta bursts, they did in fact correlate with increasing motor severity in Parkinson's. So now we have another part of the beta signal that in fact might be useful as an input for closed loop deep brain stimulation. But more than that, we've now found that in fact this beta rhythm can actually help us program. And it's been shown that the DBS electrode, or you might know it as the contact on the DBS lead, that is closest to the site of maximal beta band power in the subthalamic nucleus, actually had the best outcome if it was used for neurostimulation. And here you can see the standard Medtronic or the 4-contact electrode, and the green one is the active one. So if you chose the active one or ones that showed the greatest power here, and here you can see this, that this was over these 2 electrodes in the subthalamic nucleus, you got the better outcome if you used those for active stimulation. And this was also showed when you looked at the directional lead and you looked at each of the directional contacts, and the ones that showed the highest power in the beta band also showed the greatest improvement, and in this case for rigidity. So all of a sudden, this is linking your biomarker, your beta rhythm, with actual outcome, is if that you use this, if you go and stimulate in the site of the SDN where you've got the maximum beta power, you'll get the better outcome. And this, of course, could drastically improve the time that it takes to initially program a DBS device. Now, another thing that Kevin Wilkins did in my lab was to look at that precise question. We can use deep brain stimulation basically as a tool, because what happens, as most people know, is as you increase the intensity, the voltage or the current in deep brain stimulation, you increase the volume of the field, the electrical field in the brain. And you can use this to ask this question: does the volume of the field, or the percentage overlap of the field with that sensory motor region in the STN and the STN proper, does that actually matter for both attenuating those beta bursts and improving motor function? And they did a lot of work with this, and I'll just go straight to the final slide, which was indeed, we showed that the greater overlap of this volume of tissue activation, or VTA, the field, with the sensory motor region, also the greater the degree of the reduction of the beta band burst duration resulted in the greater improvement in bradykinesia. So now we have direct evidence that in fact this beta band burst duration, and of course your accurate lead location, will in fact be good inputs and strategies to get you the best outcome. So let's move on to how we're going to incorporate this into what we call adaptive or closed loop deep brain stimulation for Parkinson's disease. So as I mentioned, as you increase the intensity of deep brain stimulation, and here we use the clinical voltage that someone was on with the legacy leads of Medtronic as the 100%. And we then applied in a randomized order different percentiles of this. And you can see that with no deep brain stimulation, here's your alpha beta oscillopathy, so this big peak over the 1/f curve. And when you go to about 25% of your Vmax, or your clinical voltage, there's really not much change. But once you get up in the higher currents or voltage, you see this nice dose-dependent attenuation or reduction in beta band power. Now, interestingly, what we did in the lab is we said, okay, what if you give somebody a dose of levodopa? What happens to beta if you measure it over time? And here you can see that as the medication kicked in, beta band power decreased and then increased again as medication wore off. So now you have both of the therapies that we use in Parkinson's disease, both attenuate this brain rhythm or this biomarker. However, up until now, we've never been measuring this. And that would be an analogy here is if one of your family members was being treated for high blood pressure with 2 medications, both of which decreased your blood pressure, but you never measured the blood pressure, you could imagine that one could get into complications of overcorrection or undercorrection. And we think that that might be one of the problems about using DBS and medication without being able to measure this beta band power. And so continuous or open loop DBS would literally be on all the time at the same level, would be blind and deaf to what's going on with the beta band power. But if you have adaptive DBS, it could sense when the beta band power is being reduced due to the onset of medication, and it could adapt its own stimulation intensity down, which would basically drive you up here. And so you basically keep this beta band power within what we hope is a therapeutic range that doesn't change too much. So this brings us to how do we do adaptive deep brain stimulation, and something that we developed, which we call the dual threshold mode. And this is quite simple, but it's a little bit of a brain tease because you have to think about this inverse phenomenon, is that as you increase voltage or current along the x-axis here, you decrease beta band power. The most important thing that I'll get to in a minute that you want to do is you want to make sure that if you're going to let the voltage or the current change automatically, you want to make sure that it's going to change within what we call therapeutic limits. So you don't want to go too low and you don't want to go too high. And so what you do is you first set what that upper intensity is, which we do in standard programming. We go up to the current or the voltage above which you start getting side effects, maybe some pins and needles or some pulling, and we don't want to go up there. So we call that, okay, that's the maximum voltage we can use. And then we measure the corresponding level of beta band power. Then importantly, which I'll show you in a minute, we want to develop what is the lowest intensity that we'll let this go to, because we don't want it to go down so low that every time it fluctuates down, you're going to get tremor back or you're going to feel stiff or so. So we want to find an acceptable lower limit. And then these are the limits we're going to choose between which the system can basically fluctuate. And then we measure the corresponding beta threshold. So the beta level that corresponds to the lowest acceptable level of intensity is our upper threshold. So again, flip these. And then for us, we use the lower threshold as the one in between the two measures of beta power that corresponded to VL and VU. And what we said was we asked the stimulator, and again, we're writing these automated algorithms, if beta power goes above this upper threshold, we want you to increase voltage. If it's in between, we want you to stay the same. And if it's below the lower threshold, we want you to decrease voltage. And here you can see, here's the upper beta threshold, here's the lower beta threshold, here's beta power fluctuating up, above, and in between these thresholds. And this is exactly what the system is doing now. It's going up, it's staying the same, it's going down, it's staying the same, and it's fluctuating the level of intensity. And I just drew in the dashed line as this is what your current open loop or continuous level of intensity might have been. So you can let this fluctuate up and down below what you would be in what we call the open loop intensity, as long as these are safe limits for the person.
And could I just ask a quick question here, Dr. Bronte-Stewart? Is that on the left diagram, is the blue line the same for everyone, whereas VL, VU are different for everyone?
No, they're different. So this is this has to be done on patient specific, participant specific, because the blue line here is actually how beta decreases with increasing intensity that it's not a straight line. There tends to be this kind of exponential shape here. And so it is different for everybody. And that's why we do very careful titrations with every person. And that's something that will be part of the adaptive DBS protocol, is that you want to make sure you know for each person, what is this as far as safe limits, and then what does this correspond to? And you don't obviously need to map out this whole curve for every person, but you want to know what are these levels individually and set them individually as your thresholds. And they do differ.
Okay.
Now, another way of doing this is to use a single threshold. It's a little harder to show, but basically you have just one threshold. And if the beta band power goes above it, the system then ramps from the lowest current or voltage up to the maximum. So this is a very different kind of prospect. The system just goes straight from Imin to Imax. Here you can see some people call this the thermostat approach. If this is Imax and Imin or Vmax and Vmin, it doesn't do that. It kind of, fluctuates around in between the two. This one goes up, and then if the beta band power is above the single threshold, it stays there. And when the beta band power goes below the single threshold, it ramps down. So this is a different way of doing it. And this was the one that was originally published in 2013 by the group in Oxford. And so here you can see just a schematic of how this would work over time, which you can see is very different from how the dual threshold system works, both of which work, by the way. So here I'm getting to Robin's question, which was, how do you do this? Well, you do this with each person as an individual. And what we do is we link the neural recording with the movement recording so that we know that what we see happening in the movement is in fact linked in real time to what's happening with the neural signal. And so here you can see again, we're using this Vmax of the clinical voltage, and we're applying in a randomized presentation different intensities of deep brain stimulation. And now during that repetitive wrist flexion extension task, we're measuring the angular velocity. So we're basically measuring bradykinesia here. And as one would hope, as the current goes up, the person gets better. But what's the lowest but acceptable range that somebody would allow the system to go down to that wouldn't be intolerable? And here you can see that our team have plotted these average numbers of the velocity of movement. And you can see that often, even on those low currents or voltages, people don't really tend to get better. But as they get above 50%, then they get into what's called this therapeutic range. So once we do that, we can set these limits. And then we have to do something that's also very important, is what we call ramp rates. And that's how quickly does that stimulation increase and decrease. And this will depend on the goal of therapy. So if, for instance, you're trying to adapt the system to take into account that slow drop of beta as medication kicks in, which is over the period of 15, 20 minutes, you may want to use this longer ramp rate or a slow adaptation of beta responding that will respond to the onset and offset of beta modulation from individual doses of medication. You may want to use faster ramp rates, rapid adaptation, if you're trying to respond to something that happens rapidly, like tremor or gait impairment or freezing of gait. We often set the ramp rate down longer or slower than the ramp rate up, because if we go down too quickly, we sometimes can kind of evoke a rebound of beta that then might mean that the system responds to that when it shouldn't. And it's very important to determine what's the maximum ramp rate somebody can tolerate, because an increase in ramp rate that's too fast, that we sometimes see when we go up too quickly in the operating room, may actually itself lead to adverse effects that has nothing to do with that volume of field that's maybe affecting another structure. There's something about the brain doesn't like too rapid an expansion of a field. And as for those of you who know, who've gone through this, we go very slowly in the operating room in order to not get into that problem. So we don't want it to go up too fast for somebody, because then they may feel adverse effects every time it adapts. And one of the things that's really important in the single threshold mode is I showed you that it adapts up and down and up and down. And we call each time it does that trapezoidal adaptation a duty cycle. And if that happens very rarely, then the person can actually feel the ramp up. But if it happens about 50% of the time, it's so interesting. The brain adapts and the person doesn't feel it anymore. So that's another variable we look at when we're looking at the single threshold mode. And that will also be happening as this rolls out when you're being programmed. So this is just to show you that I showed you what we call titrations using the repetitive flexion extension with a wearable on it. We can also see this using our QDG device. And this is somebody off stimulation. And here's one finger pressing down on the key, the other finger pressing down on the key. And this person's doing very nice full amplitude tapping, but it's quite slow. And you can see, again, we can determine the most acceptable limits by looking at their QDG output as they get faster, as we get up in intensity. And we also can do this in this stepping in place task, where, without going into the details, every time in between these green circles is our computerized identification of a freeze. And this is when the feet aren't actually getting off the force plate. And then as we increase the intensity, you can see there's some nice full stepping where the feet are coming off the force plate. And this gets better as the stimulation improves. So we can see this in all modalities, in fine motor control, in limb motor control, and also in gait.
And Dr. Bronte-Stewart, a couple of relevant questions have come in about that ramp rate. Can the ramp rate respond to something like tripping or falling fast enough for someone to get to protect their head by getting a hand out to catch their fall? Or is a fast ramp rate more in response to freezing so the person can get moving quicker?
Yeah, that's a great question. In evolving, DBS systems, possibly, but I think that, the fast ramp rates we use in single threshold mode of 250 milliseconds, so they're pretty fast. But the problem with falling is that once gravity's taken over, nothing you do with DBS is probably going to actually stop the fall. But you can correct the rhythmic stepping, as many people know who've been in my clinic, to get you back to do that heel strike, that long stride. You're going to avoid the fall. So we'll get to that when I talk about our study in a minute, talking about gait impairment and freezing of gait. The study we have done that I'll show you right at the end is Tremor, and you certainly can stop tremor with a rapid ramp rate.
Thank you.
Sure. This is the exciting study that has been completed as far as the primary outcome, which I can't tell you about yet, but I can tell you we're very excited about it. So this is called the APDA study. This is the first international multi-center pivotal trial, which means that it is a trial that will be then presented to the FDA to make this available to everybody. And this moved from being a feasibility trial that we're doing in America to being this international study when Medtronic found out that the regulatory bodies in both Canada, United States, and Europe all wanted the same thing. And so this has been a very interesting study where we've enrolled 85 subjects in 10 sites in 4 countries. There is what we call a primary cohort, which uses the legacy lead, the original Medtronic lead, and now the directional lead, but they have to be in a ring mode. That means, so we're not using directional stimulation. And then we used another smaller cohort who had directional stimulation. The person then had their implantation of the Percept system with either GPI or STN. They were enrolled. And then there were several phases to this. One phase was to get the baseline testing of people's motor function on continuous DBS. But of course, now what we add in these studies is we also have to measure beta band power. And we need to have enough power to be able to drive adaptive DBS with beta band power, which was what the neural input was for this study. And then what we did, we had a 2-month period where we set the person up on both single threshold mode and dual threshold mode sequentially. And people would go home for a little while, come back if it wasn't quite right, we'd adjust it until we were all very comfortable that they were good on both modes. And then they were randomized and they did a single blinded, what we call crossover design, that some of them started on dual threshold mode and went home for 30 days. And then at the end of the 30 days, the primary outcome measures were evaluated. They also filled out diaries and wore a watch. And then they changed to the single threshold, or they might have been randomized to the single threshold mode and then moved to the dual threshold mode. And then they were asked if they would like to enter an open label long-term follow-up phase. And some people could not tolerate both modes, so they would only do one mode. So this was a really exciting study that suddenly pushed adaptive DBS into going home with it, which, none of us were doing in our NIH trials. And it's all been tolerated extremely well. And just to let you know that only one person out of the cohort who finished this, which was 45 people, wanted to go back to open loop. So 44 out of 45 people continued on adaptive DBS. We were lucky enough to recruit the first person in this trial who was recruited in December of 2020. So it wasn't on adaptive DBS right away, but is still on adaptive DBS. So we're going to really be excited to be able to tell you the primary outcome, which the FDA requested, that this was an equivalence in numbers of people who had a certain percent time on without troublesome dyskinesias that was equivalent to what they were in their open loop or continuous or clinical DBS setting. We met those outcomes with both modes. We exceeded those outcomes, and there's some very interesting data with that, but that will have to wait for a little while before Medtronic will allow us to actually present the results. They were presented. I presented them for the first time at the DBS think tank last week, and they will be presented in a poster format at movement disorders meetings next week or the week after. But they're not allowing us to do this yet in sort of non-scientific forums. So I'm sorry about that, but that's all because they need to be very careful with the FDA, and we certainly don't want to mess up that process. So I'm going to move to quickly talk about our own closed loop study or adaptive DBS study that we were very lucky to get funding from the Brain Initiative for, and we're very grateful to that. And as some of you who might be part of this know, this is now in year 4. And based on all the work I've showed you, we now have 2 inputs that we're using. So we're using a neural input, and here because we're using the Investigative Summit neurostimulator, we actually can get down technologically to measuring whether a burst is normal or abnormally long. And in the kinematic input, we're using a measure. This is getting sort of to what Robin was talking about. We're getting to a measure of gait that's abnormal, which is gait arrhythmicity, that can actually predict freezing. And we're also using another one, which we determined from some modeling, which was sort of a freeze probability. But interestingly here in the neural system, we're adapting intensity only, as I showed you in those figures. But in the kinematic, we're adapting intensity, but we're also switching frequency, because some people do better with low frequencies with freezing of gait than others. So very complicated study, but we're moving through it. And just to kind of show you the early data out of this, here you see the single threshold mode now looking at beta band burst duration. So here's our beta rhythm. So this is filtered in the beta frequencies. And here it goes up above the threshold and stays above there, and then goes down below it. You can see this. So what our algorithm is saying is, okay, this duration above here is normal, but as soon as you get into the red zone, that's abnormally prolonged. And then what the system says is, okay, when it's abnormally prolonged, let's increase stimulation intensity. And don't worry about this so much. We have certain delays in there to stop it overreacting. And so what you can see here again is, here's that raw signal I showed you with a local field potential. Here's it filtered in the beta band power. You can see these nice bursts going over this threshold. Here's the algorithm saying, okay, this duration is normal. This is too prolonged. And what the system does is when the burst duration goes into the red zone, the Summit system responds by increasing stimulation intensity, as you can see here. But when it detects only very short duration bursts, it says, okay, those are fine. Let's start decreasing stimulation intensity. So we've shown now that this works, and this actually does improve gait impairment and freezing of gait. And Matt Petrucci in my lab published a case report showing this, in fact, using that stepping in place task on our force plates. And here's somebody off their medicines, and our computer algorithm says, oh, here's a freeze. And the reason we know it's quite easily that we know this is a freeze is that we normalize the force that the foot exerts on the force plate with their body weight, so that when it's all at 100%, we mean the weight is all the way on that foot, and the other foot should be off. So we should see this nice out of phase sinusoidal 100 to 0 for both feet. This person's going so fast you can't detect. There are actually 2 traces here. So when you see something like this, the foot hasn't come off the force plate, although there's still weight shifting going on. And so this is a freeze. So the person's not getting their foot off the force plate. What we can also measure is basically how rhythmic is this stepping. And you can see that over time, this is very arrhythmic. And we can measure that and call it arrhythmicity. When we have them on their open loop, normal clinical stimulation parameters, they do much better and they do very nice stepping, but then it starts breaking down again. And what we needed to do, if we're going to compare apples to apples, is we needed to convert how they were programmed in the open loop mode to how similar it would be in the closed loop mode. And this is that we can actually only use one active contact. So what Matt and our team did is they then did short runs of adaptive DBS to determine roughly how much voltage would be applied. And then they set this person up on a single active electrode with a certain voltage that was going to be similar to adaptive DBS, and then ran it in an open loop mode. And you can see, again, they do pretty well at the beginning, and then they begin to break down with some freezing, and they're not even quite as good as they were with their regular clinical parameters. However, when you run the same system in an open loop, in a closed loop mode, meaning that the system is responding to that beta band power, all of a sudden you can see that apart from a little start hesitation, there was no freezing at all. And when you measure this arrhythmicity, this abnormal rhythmic gait, you can see that in the off stage, the higher the value, the worse you are. So they were already quite arrhythmic to start with. All forms of DBS in the first 25 seconds drop their arrhythmicity almost to zero. So very nice stepping. But in both of the open loop modes, this arrhythmicity got worse over time, whereas in the closed loop mode, it actually stayed nice and rhythmic. And this is one of the things we'll be really interested to see as adaptive DBS people are on it for longer and longer periods, whether in fact that's what we're seeing, is that it's this stability over time that might really make people prefer it. So very early studies, early responses. And this is basically just saying what I said before. So this is a complicated slide, so I'm just going to tell you what not to look at. Don't worry about this. This is actually the setup with the person with wearable sensors and the fact that we're recording the kinematics now, and we're taking them through our algorithms, and we're telling the stimulator what to do. This is a nice diagram of where their lead is and where their volume of tissue activation or the field is. And now what we're looking at, again, as I said, is this is the single threshold mode using gait arrhythmicity. And basically the algorithm goes back and sort of measures what's been going on in the 3 to 6 steps prior to making what we call a state decision. And as the arrhythmicity goes above this single threshold, you can see that the system says, oh, this looks like there's going to freeze happening. Let's increase the stimulation intensity. Whoops, sorry, I pressed the wrong one. Nope. Hold on. Okay, sorry about that. And here you can see the traces. Again, when the person's off their DBS, they're not doing too well. They've got a long freeze here, then arrhythmic stepping, open loop, as they are currently in the clinic. Again, first 25 seconds or so, they do really well, then it breaks down. And then I'll go straight to the adaptive deep brain stimulation. You can see that they do well for a longer period of time. What we were asked to also say is, okay, maybe just adapting deep brain stimulation without it being reflective of the actual gait parameters, maybe that's just better than it being on continuously. So in our project, we have what we call a control scenario where we do intermittent open loop DBS. So we vary open loop DBS, but not based on the neural or the kinematic parameter. And you can see that even though we're having intermittent stimulation, just like we might have with adaptive DBS, it really needs that biological signal to drive it to do better. And so here we are in that arrhythmicity. We get all forms of DBS really improve, but there was a suggestion that adaptive DBS was better, and the percent time freezing went down to 0 on adaptive DBS. So, this is one patient for each one of these things, and we're working on trying to we'll publish the whole cohort, but so far we definitely see that both neural and kinematic inputs can be used for adaptive DBS. They work, they improve the abnormal parameters we're trying to improve. And then finally, just to show you Tremor, this was actually the first adaptive DBS paper we published. And here we're using a watch that's measuring tremor, and we're again feeding it through this system to drive stimulation. And here you can see it working. Again, we do a calibration period where we measure tremor power. We develop these 2 thresholds. You can see the upper one in light blue, the lower one in magenta. The system increases voltage when the tremor goes above the upper threshold, stays the same between the thresholds, and goes down when the tremor is below the lower threshold. Often what we see with DBS, with tremor, is that it doesn't often stay within these thresholds. So you can see this is basically a demand brain pacemaker. And over the cohort, there was a significant reduction in tremor. And in fact, it used 76% lower voltage on ADBS versus CDBS because it wasn't needed all the time just for tremor. One of the things that was the most fascinating to me was that everybody's tremor is different. Some people, as soon as the stimulation ramped down again, their tremor came back and they basically needed it on most of the time. But there was other people like this person who had very intermittent tremor, and you can see that they really didn't need DBS for a lot of the time. And so for them, if they didn't have a lot of bradykinesia and rigidity, they don't really need continuous DBS. They may just need a demand stimulator, just something that responds when they have tremor and goes away when they don't. So this was the fascinating thing we saw, that on average, the time on was about 50% of the time on open loop DBS, but this was very variable and really required patient-specific calibration. So I'm going to move now to some quick conclusions, if my slide will work. So successful deep brain stimulation, as we said, requires well-characterized patients and accurate lead placement in well-defined circuits. Successful adaptive DBS requires neural or behavioral inputs that are relevant to what we call the pathological behavior, or the symptoms we're trying to improve. Local field potentials demonstrate exaggerated neuronal oscillations and excessive signaling, which we call oscillopathies, in the sensory motor network in Parkinson's disease. It's a feature of the hypokinetic aspects of Parkinson's disease, bradykinesia and rigidity. It's maximal or optimal sites for stimulation in the STN, and it's attenuated on therapeutic doses or intensities of medication and deep brain stimulation. The clinical usefulness of recording local field potentials from the implanted stimulator includes improved optimization of programming, as well as determining these relevant neural inputs for adaptive DBS. And synchronized kinematic and neural recordings can reveal the neural and kinematic features that are relevant to movement disorders. And both neural and kinematic adaptive DBS is feasible. It improves tremor, bradykinesia, gait impairment, and freezing gait in Parkinson's disease, and more to be discovered. So this is just to thank the current and former members of my lab and our collaborators, and most especially to thank all the people who have volunteered so many hours of their time, especially the people who've been sitting with us since 2013, determining all these relevant neural and kinematic parameters, and the people who've started with us in our adaptive DBS projects. And of course, a big thank you to our funding sources. And I will then hand this over. We are recruiting for our next phase of the spring study, which will use Percept and we'll use some at-home testing. And we're also testing our QDG system, which we've upgraded the device, and we're now turning this into a remote monitoring system. And we're looking for people who'd be interested in being partners with us as we do the first remote testing and get some feedback from people of what they like and what they don't like. And so I'll take some questions and then hand this over to Laura and Arushi to discuss further. So I'll maybe just stop sharing so that we can see.
Okay, thank you, Dr. Bronte-Stewart. Wonderful talk. Quite a few questions came in, and please, if anybody has questions, use the Q&A box or the chat box. One question was, is adaptive DBS similar in any way to the NeuroPace RNS for epilepsy?
Yeah, that's a brilliant question. Yes, but the RNS system can record the electrical rhythms, the EEG, and then it stimulates. What we do is we record during stimulation as well. So yes, it's an adaptive system, but once it stimulates, it stops listening. Whereas the adaptive DBS system that we are using, it listens the whole time and adapts during stimulation.
And for that kinematic monitoring you mentioned with the wearables, either something on the foot or a watch, I think was the other option. Do you envision when this is made available to the general public that those wearables would be worn over the skin as they are now, or how would that happen?
Yeah, so this is the interesting thing, I think, of working in collaboration with industry, the NIH, the FDA, and academia, is that we sort of each push each other along. we have been very excited about using kinematic inputs, but the system that is going to be, hopefully, if the FDA approves it, available to everybody is not going to be able to sense kinematic inputs. And why is that? Well, because you need a Bluetooth system within the device, and there's an enormous worry about cybersecurity and various systems like that. So it's very appropriate and very real. It's very sad for those of us who are doing this work and showing that it really would be great to have what I call a hybrid system where you could do both. And then that would spur also technological development of very small sensors that would just sit under your clothes, things that you don't need to wear this big clunky thing on your legs. However, there are other countries that are developing other stimulation systems, but this was something in the meetings we were at last week that was really brought up by the ethics groups. And I think it's very important that we go through all of this and try and figure out how can you do this safely. And of course, with the financial outlay that some device company would have to do, is it really going to be better than using beta or beta band bursts or another rhythm that is being looked at with other disorders? So that's kind of where we're pushing the frontier of this by doing this in the lab, showing that it works, using what we call these distributed systems. But to translate that into clinical practice, we have a whole bunch of other things that come in that we, meaning everyone, all people with Parkinson's, the researchers, FDA, NIH, industry, everybody has to get together and really figure out how can we do this safely? Is it worth it? Is it worth the expense? So I think this is something that is very important to talk about, but unfortunately not available just yet.
Yeah. Another questioner asks, about how long will this take to be approved for the general population? Common question.
Oh, the big
And
question.
I know you're waiting too.
So yes, right now, we thought that the Percept rechargeable would have been available in the spring, and poor Medtronic, every time they go back to the FDA and answer a question, there is actually a 6-month period that the FDA has to come back to them, which is what I found out why it's taking so long. It's nothing to do with the FDA. The FDA are great. They give us responses in 30 days. This is a problem. So it's taking a long time just to get Percept into a rechargeable, approved as a rechargeable device. But we are, so I'm helping Medtronic with developing the material that will go to the FDA, and they were hoping to get this in basically by February. It's unclear, as you can imagine. There's an awful lot of work they have to do to get that everything together. So I think it, I was hoping that this time next spring it would be available. We know the results, we know it works. That unfortunately may take longer. So don't hold your breath over this, but it's going to go to the FDA. We're very excited. We're very hopeful, but you never know what the FDA might want. And I have huge respect for the FDA. So, there may be some other things they need to do. We don't know. This is a big change, as you can imagine, for the FDA to say, we're going out and somebody's automatically changing your stimulator. We want to make sure that's absolutely safe. But we are doing it in our own trial that Laura and Arushi will tell you about, and in ADAPT. So they did go home. We do know it's safe, but that was under very careful trial conditions. So we want to make sure that the FDA feels that all the I's are dotted and T's are crossed before they approve it.
And what you've gone to the FDA with is that 85-person study, the multi-center study.
Yes. They wanted, so we added the directional cohort later because we didn't have the directional leads right away. And it would be very sad if it got approved for the old leads and then nobody used them anymore. So so we added the directional cohort as another cohort to show that it would and we don't know the results of that yet. The results that we know of are the primary cohort. So I can't say for those ones.
Right. Someone asks, how is this, I'll just read the question. How do you, once you've determined the upper and lower thresholds, or it is determining the upper and lower thresholds all done by mathematics, by algorithms inside the system, and then the system itself makes the adjustments based upon
Yeah.
those thresholds. Wow.
Yes. In the
Yeah.
lab, we do what I showed you. We do these
Yeah.
titrations. In the APDA system, we do it slightly differently. It's all within the device. When they are working on making that sort of easier to use if and when hopefully it's approved. But it will be done, it will be fairly simple to do. It will require obviously that the clinician and the patient determine those stimulation limits, and then the system will automatically measure the beta threshold that
Okay.
corresponds to those.
Yeah. Okay. I'm just looking at other questions. If there are any other questions coming in, please use the Q&A box or the chat box. So someone asks, can someone with open loop DBS, and I think they meant to say, well, can someone with open loop DBS be upgraded without a new brain surgery?
That's a great question. Yes. So the Percept system, if somebody has now, if you use a Boston system or an Abbott system, no, currently, because they're not sensing devices, unless you use the Boston leads. No, in fact, you can't do that. Yeah. So we have had people who have Medtronic leads and have a Boston IPG, but it can't work the other way around. So the Medtronic system with Percept currently has all the software in it to do adaptive DBS. It's what we call unlocked for research purposes. So the goal will be that they'll have devices that are all ready to be used for adaptive DBS, and when it's FDA approved, they will be unlocked. There may be a new programmer, there's new what we call firmware, but it won't be a new surgery unless they don't have a Percept system yet.
Right. Okay. And how long has the Percept system been available on the market?
I was using it. It's been for at least 2 or 3 years. I'm so used to I've used it all the way through because it was the Activa PC+S system that then was commercialized. So I can't remember the actual date it was.
Okay. But there are thousands of people.
Oh yeah. It's been available for a long time. Yeah.
Okay, fantastic. Yeah. So then once it's FDA approved, all those people would be in theory eligible based upon the system that they have for the turning it.
That's my current understanding. I don't, it depends. I mean, that's my current understanding. And hopefully at some point we'll have the rechargeables.
Right. Okay. Any more questions or chats? I'm just looking here. Yeah, anybody, one question I thought of was, what made, you said one person out of the ADAPT PD decided to stick with the with the old system. Do you have any insight into why? No. Okay.
No, and if I did, I wouldn't be allowed to say. So
okay. All right. Okay.
we're in this study, all the data is analyzed and kept at Medtronic. So we don't necessarily, I do know some of it, but I can't say anything about it. So.
And you're probably blinded to the individual.
Oh yeah.
Distance anyway. So yeah. All right.
I know my cohort very well, but no, none of us know each other's. Of course, it's all de-identified information.
And how many centers have participated in the ADAPT PD? 10.
Centers in 4 countries.
Okay, fantastic. Okay, somebody asked, has there been any non-motor effects of using adaptive DBS?
Very good question. In the adjustment phase, it's rather like, it's not going to be different in a sense from regular DBS programming, meaning that you're still sitting in the same place. Your field is going, the volume's going up and down. So what you want to make sure is that you don't get at its maximum volume at Vmax or Imax, you're not encroaching on other structures. So we know that from initial programming, we have to make sure that somebody isn't having pins and needles or isn't having pulling of the face or isn't having speech problems, or sometimes there might be lightheadedness or even sometimes some vertigo. So it's the similar symptoms that you'd be checking for in initial programming and making sure your static field with open loop is not encroaching. But now, because we're allowing it to fluctuate a bit, especially with that single threshold where it literally goes up, stays the same, and goes down, we want to make sure that we don't induce those side effects. And so, yes, some people, when it wasn't adapting at 50% duty cycle, one of the things that one of our people told us was they felt lightheaded. They kind of, as they were walking around, they were like, oh, I feel lightheaded. And then, oh, I feel like, and it was time to when we were watching, it was going up and down. So you definitely can have non-motor side effects depending on what structures the field may be encroaching on. So we look for those in regular programming. We have, just like we do with medication, we have what we call non-motor offs. So we know that there is some non-motor aspect that's even accessed by these dopaminergic types of therapy. Yep.
Okay. Any more questions? Oh, here's one more came in. Did some of the study individuals use time release medications such as Rytary or Gocovri?
So we don't know that yet in the whole group, but yes, they were allowed to use any medication that they were on. Originally, they just had to stay on the same dose once they were in a certain part of the study. So we didn't want to compare, say, when they were on meds and on continuous DBS to the outcome if their medications changed in between, because obviously that would affect their motor outcomes. So we were asked to stay on the same amount of medication and keep that a constant so that any changes were due to DBS.
Okay, interesting. All right, any more questions? All right, and we're just a little bit beyond 1 o'clock anyway. Thank you so much, Dr. Bronte-Stewart.
Most welcome. And I apologize, I have another meeting, so I have to jump, but you're in wonderful hands with Laura and Arushi.
Yeah, very good. Thank you so much again.
Bye,
okay,
everyone.
bye-bye. Bye-bye.